Welcome to Ask and Learn.
In this problem, we have 1 ton of liquid water at 50 degrees Celsius, which is brought into a room, and we want to calculate the final equilibrium temperature in the room. We assume that the room is well insulated and well sealed, and the thermal properties of water and air are constant. Now, the gas constant of air, R, is 0.287 kilopascal meter cube per kg Kelvin, and the specific heat of water at room temperature is 4.18 kilojoule per kg degree Celsius. These we get from our tables. So to start off, let's find the volume and the mass of the air in the room. Now the volume of air is the dimensions in the room, which is 4 times 5 times 6 in SI units, which are meters, so the volume of the room is 120 cubic meters. The mass of air occupying the room, we use the ideal gas relation P1 V1 over R T1. And again, we can calculate this since we have these values. So the pressure is 95 kilopascals. The volume we calculated to be 120 cubic meters over the gas constant for air at room temperature is 0.2870 kilopascal meter cubed per kg Kelvin, and the initial temperature of the room is 288 Kelvin. So the mass of air in the room is 137.9 kg. So we have the volume and the mass of the air. Now, if we take the contents of the room, including the water as our system, we can write an energy balance equation. Since this is a closed system, E in minus E out is equal to delta E, the change in energy for the system. So since there is no heat, work, or mass transfers, the left-hand side of this equation is 0, and this is equal to a change in internal energy of the system, delta U. But delta U is the change of the internal energy, delta U, for the water plus the change in internal energy for the air, delta U for the air. So what this means is that, remember, a change in internal energy can be related to a change in temperature, mc into the final minus the initial temperature for water, plus we'll write for air in the same form, the term mc delta T, mc into T2 minus T1, and that's for air must equal to 0. So from here, we can actually rearrange this equation and solve for T2. So T2 is actually the equilibrium temperature of the water, of the air in the room, the water in the air system. So let's substitute our values in here. We get the mass of water, 1000 kg, times its specific heat at room temperature, 4.18 kilojoule per kg degree Celsius, times the temperature change of T2 minus the initial temperature of 50, and that's degrees Celsius. Remember, this is for the water, plus the mass of air we calculated to be 137.9 kg times specific heat for air, 0.718 kilojoule per kg degree Celsius, and this is multiplied by T2 minus the initial temperature of the air, 15 degrees Celsius, and that's all equal to 0. So If we rearrange this equation, we can see there's only one unknown here, which is T2. We can solve for T2, which is the equilibrium temperature of the system. And T2, if we solve this equation, becomes 49.2 degrees Celsius, which is the final equilibrium temperature in the room.